this interaction. And in continuation to yesterday's interaction that we have had, we were talking about the commutation relations, and we started our discussion in obtaining some of the important basic commutation relations between position and linear momentum. And we generalized that result. And today's target is basically, we have a target of starting with the commutation relation between the position and angular momentum. But before we talk about these commutation relations that we would be solving, I would like to get a feel of this angular momentum. And obviously we are in a context of deliberating our understanding, which is freak weird when we compare it with the classical laws of physics, and when we compare it with the classical bodies like Earth, Moon, solar system, a galaxy, and a universe. So to begin with, if I start with an argument that I'm the one who is trying to understand the two frameworks, and what I have here, I would like to have two characters. The character 1, I will name this character as, say, Classica. So I have a character 1 as Classica, and I have character 2 as, say, for example, Quanta. So I have chosen two characters, Classica, this is character 1, and then another character as Quanta. These are the two characters, and myself trying to understand the Classica and the Quanta. What Classica is carrying a spherical ball with well-defined shape, and on the other side is Quanta, and Quanta is holding a cloud kind of thing, a cloud-shaped object. It seems to be weird when I see towards the Quanta. So when I talk to the Classica shows me that there's a particle. It takes a particle and clings this particle to a rope, and then rotates this particle. And it tells me, the Classica tells me that I am the classical angular momentum. And if you want to define me, the Classica tells me that I am simply the cross product of the position vector of the body and its linear momentum. So here things are very clear. I can see, I can watch every moment of this object that has been clinged to this wire or a string. It's roaming perfectly, and the Classica is telling me that you can exactly see all the axes that I carry. Now, if I replace this particle by a hard spherical body, it will have three axes, say X, Y, and Z, and I can sharply see what's going on, and I can see that the coordinate X, the angular momentum along X, has a dependence on angular momentum Y, has a dependence on angular momentum Z. They seem to work together here. So when there is rotation happening in the framework of Classica, everything is clear, everything is distinguishable, and for the fact of matter, everything is continuous. The angular momentum is continuously changing. And what angular momentum is telling me? Angular momentum is telling me that I am the one who is perpendicular the plane that's carrying the position and the momentum of the particle. And what the angular momentum does, it makes an impact on the position while making that rotation. And that impact is continuous. There is continuously a changing angular momentum of that body, of that particle. Now, I go to the other side. On the other side of mine is quanta. And quanta is showing me a kind of cloud is there. There's weirdness, there's confusion. And when I tell quanta, can you demonstrate yourself in front of me? The quanta says, come on, I can demonstrate myself in front of you, but what I'm something that's weird in nature. I'm something that's quantized in nature. And here, when I talk to the quanta reacts and tells me that you cannot find me continuously changing. You can find me in packets. You can find me transforming. Here, in case of classica, there is continuity, there is continuous change. But here, in case of quanta, there are jumps. There are jumps of angular momenta. There are packets of angular momenta. Here, in case of quanta, we have the transformation. But here, in case of classica, here is the continuity. So the point is that you can demonstrate the problem that we have, the angular momentum that this quanta possesses. We can learn about the angular momentum of this system and its commutation with the position or with itself. For that, I need the quantum mechanical operators, and here I can make calculations, and all these calculations are directly coming from the observables that we are interested in calculating here. So the point today that we have is that this quanta can be resolved, and when we resolve the commutation, because we have already talked about the commutation relations, we have tried to understand the commutation relations in the framework of that box I was talking yesterday, which has two locks. One is a golden lock and another is a silver lock. And we could easily demonstrate this hypothetical experiment to realize what commutation means and how we can realize that the order of action in quantum world is very, very important. It is the order that can change the geometry of the outcome of your problem. If you rightly remember the galaxy that I was talking about in that box, this box was held by Imran, and we could see, if we first open the silver, then the gold lock, we could see a galaxy which is cool, which is beautiful, which is symmetrical. Everything is cool and calm going on in that galaxy. But if we open the same box, but first we open the golden lock and then we open the silver lock, we see the violence. The galaxy is very violent. There is nothing symmetrical. Everything is asymmetrical. This is how commutation relations work out. So today we are going to go with the angular momentum, and from its basic definition, we know what angular momentum is. If I write down the angular momentum, it is the cross product of the position vector and the momentum vector. But here in quantum world, we are very much interested in the operators, because in quantum framework, to every classical observable, we have a quantum mechanical operator. So what we can do here is we can choose this R in Cartesian coordinates as xi cap plus yj cap plus zk cap. And this will be my position vector R, and the linear momentum in terms of its components can be written as px I cap plus py j cap plus p zk cap. And as we understand from the basics of the cross product, if I have to take the cross product between these two physical quantities, I can use the determinant. So I can write down this angular momentum vector as a determinant of I, j, and k. Then you'll have x, y, and z. Then you'll have px, py, and pc. So what we can do here is we can replace our positions by their corresponding operators. The momentum along x, y, and z, I can replace them with respect to their operators. As we know, we can replace this px by minus ih bar dou by dou x. And similarly, we can go for py and we can go for pz. And what we will do, we will evaluate this determinant. And when you will evaluate this determinant, or if you know how to evaluate it, so there are many ways, and you can choose any of the ways to solve this determinant. So the first one you can use for I, and then you know how to boil down this determinant. So once we boil down this determinant, what we obtain is, in the left-hand side, what I have Lx I cap plus Ly j cap plus Lz and k cap. So what we are going to obtain from this is the angular momentum x operator, and this will come out to be minus ih bar y dou by dou z minus z dou by dou y. So this will be our angular momentum operator along x-axis once you resolve that determinant. And similarly, we will have for Ly. For Ly, I'll have minus ih bar, and I'll have z dou by dou x minus x dou by dou z. So this is another operator for angular momentum. Sorry. And finally, we will have angular momentum operator z, and this will be minus ih bar and x dou by dou y minus y dou by dou x. So now we have the presence of these angular momentum operators for all the three coordinates. Now, what we want at this point of time is we want to obtain the commutation relation between, say, we will take on the position and the angular momentum along x. Let's take the first exercise, that I would like to calculate the commutation relation between position and the angular momentum along x. So this will be our first job. So here what we have, here we have commutators, and when you write down this commutator can be written as Lx cap minus Lx cap x. This is how we can write down the commutation between the position x and the angular momentum along x. So now we would like to use the operators that we have already written. So what we will have here is we will have x times, one thing is clear, that minus ih bar is going to be out. So what you will be left inside with is Lx, and Lx is already written down, and what is that? That is y dou by dou z minus z dou by dou y. So this is the first term, and we would like to write down the next term as minus, because we have minus, and minus IH bar is common to both, so this minus IH bar is outside the whole bracket. So what you will have now is, you have first the operator. So you have what it is, we have y dou by dou z minus z dou by dou y, but this has to be multiplied by this x. So then we have the long bracket. So now what we are going to do is, we will introduce the eigenfunction. Okay, we will multiply this by psi, and you can multiply this by psi. So when you do this, what you are going to get, so what you will have is, you will have minus IH bar is out, and then inside you will have x, and I'll have to check it, x y dou by dou z. So this is x times y dou by dou z minus z dou by dou y. I am multiplying this by the eigenfunction psi, multiplying this by eigenfunction psi. Okay, this will be the first thing. The second thing will be, in the second case, what we have the operator first. This is y dou by dou z of x and psi. This will be the first term, minus z dou by dou y and x psi. This is how it will work out. And then you will have the long brackets like this. Okay, this is how it will come out. Now we can see here what we will have. The first term here is directly xy dou psi by dou z. The second term will be x z dou psi by dou y. But here we will have two situations where we'll be using the UV rule. Here we'll use the UV rule, and here again we'll be using the UV rule. So keeping the first things like this, I have missed the minus here, because there is minus, so this thing minus this whole thing. So if I go on resolving this part, and let me keep this part there, because I'm expecting some of the cancellations from here. So here what you will have, for this you will have y, okay, you will have y, and I can keep some bracket, x as its, into the derivative of psi will give us dou psi by dou z. Okay, that's fine. Then plus psi as its, and the derivative of x with respect to z. So they are all partial derivatives, and we should realize that x is a constant for y, and y is constant for z. So we have to take that kind of intuition here. So this is the first thing. So the first thing, this part is resolved, and then we will have this part. It has its own original minus here. So z is here, nothing wrong with that. The way y is here, and then I'll have a bracket. And what I'll do here is, I will have x as its into the derivative of psi as dou psi by dou y, okay, and plus psi as its and the derivative of x with respect to y. So this is the story, and now we have to see that what kind of cancellations we can have in this mathematical argument. The first thing you can see here is, this is xy dou psi by dou z. This is plus, but this one is minus, because outside this whole story, what we have minus. We have this minus. So what's going to happen? This term will go with this term. This will be the first thing. Another thing you can see here is, if you look at this is minus, and this minus and minus will make it plus, and it will become zx. It will become zx dou psi by dou y. Okay, here you can see this x is a multiplier here. So this is plus and this is minus. This is x z dou psi by dou y. So this term and this term, this whole thing is cancelling. So what we are left with, we are left with two terms. This is the term 1, and here you can see you have a partial derivative of x with respect to z. And x will act as constant for z because we are using the partial derivatives. So this will immediately be equal to 0. And the same story is here. This is dou x by dou y. So x will act as a constant for y because we are using the partial derivatives. So what's going to happen? So everything is gone and you are left with nothing, and that nothing will multiply this with minus ih bar, and you will come up with a 0. You will have a result that will be 0. So what I have x, Lx is giving me 0. What does that mean? That means I can exactly calculate the position along x and the angular momentum along x in this quantum mechanical framework. So no need of uncertainty principle here, because nature is allowing you to calculate these two quantities along the same direction. So this by symmetry we can say that the commutation between y and Ly must be equal to the commutation between z and Lz, and this thing must be equal to 0. So here what we have seen is when you calculate the commutation relation between the position and the same component of angular momentum, they exactly commute with each other. And the result is 0 that we have seen in the previous exercise. Now let's move on to a different combination. Now suppose I have to find a commutation between x and Ly. So I'm using the commutation between the position along x and the angular momentum along y. So how can we write this? I will write it in terms of the function. Then you will have x, Ly. This is also an operator, and when the operator of position acts on psi, you get the position. So then you have minus Ly cap and x. Right. So let's write down. Now let's resolve this problem. So what we have x. This will be acted by the wave function psi. So what's going to happen here is you have x as x and Ly. So what will be Ly? It will be z dou by dou x minus x dou by dou z. Okay, fine. Then it will be multiplied by psi, and then you have a minus. Okay, then you have Ly, and that is, as I have written that, z dou by dou x minus x dou by dou z, and this will be multiplied by this x and the wave function, the eigenfunction psi. So now what we have to do is we would like to resolve it. So in doing so, what am I going to get is, here I'll get xz dou by dou x psi. So the first term will be xz dou by dou x of psi. This will be the first term. The second term will be x Yeah, come on, come on. The second term will be x squared. So x times x will give us square, then dou psi by dou z. So here I'll have minus x squared dou psi by dou z. Okay, this is gone. Now we have to take this part, and in this part we have the UV rule. Okay, so what have I missed is the minus IH bar, which I will write at the start. This minus IH bar is common to both. So it's common to both. So this story is starting like this, and you have minus IH bar outside this. So now what's going to happen? You have minus, and then you will have z dou by dou x of x psi. So you will have minus z dou by, I have to check it, dou by dou x of x psi. This will be the first term. Dou by dou x of x psi. Okay, this will be the first term. And what will be the second term? Will be minus x dou by dou z of x psi. So you'll have minus, this minus is out, minus x dou by dou z of x psi. Okay, right? So this term, I will keep it here, and I would like to resolve this part, and we will understand that this minus is outside the parenthesis that we have here. So what's going to happen now is, what we are going to do is we would like to resolve this. So here I'll get minus, I should cut it like this. Okay, here I'll get minus z. So z times x as its, the derivative of psi will give us dou psi by dou x. Then you have minus psi as its and dou x by dou x. This is how I can write down the first term. Okay, the first term is gone. So this term is gone. Now let me go with this term, and keep one thing in mind, that outside of everything you have minus. Outside of everything from this part you have minus. So now what am I going to do is to resolve this part. Okay, so I would like to resolve this part. So I will have minus, okay, x, okay, you will multiply this, x will remain as its dou psi by dou z, then you will have plus psi dou x by dou z. And that's it. So this is the story in front of me. This I should rub off, and this I should rub off, and I'm left with this argument that I have on the board. Now I would like to see the cancellations over here, and you can see the first cancellation. This is xz, this is minus xz, this is dou psi by dou x, this is dou psi by dou x. These two terms will cancel. Oh, what's going on? So they will cancel. Okay, fine. And now we have here x squared. Do we have x squared here? Yeah, here we have x squared. But you see, minus is outside. Here it has its own internal minus. They will multiply, you will get the plus. So this term will finally become plus, and you will have x squared dou psi by dou z. So this term and this term will cancel. And that's beautiful. And then you can see here, you have the partial derivative of x with respect to z, and you can see the result here is 0, because x will act as constant with respect to z. And what is it we are left with? We are left with this term. And you can see here minus is outside, here the minus is inside, you will have plus. And plus, you will have plus, then that plus will multiply with this minus, and that will make minus. So what I'll be left with is minus IH cross minus IH bar psi. Because you can see here, dou x by dou x will give us 1. So what we are left with, the result is minus IH bar, and you have psi and something else is there. And what's that? Yeah. Okay, fine. Okay. So we have all cancellations. Anything else that we have, we are left with psi here. Okay. So what we are going to get? We're going to get psi here. In the left hand side, we have a commutation between x and ly. And you have psi here. And now you can remove this eigenfunction, and you can write down the final result as xly. And this will lead us to minus IH bar. And the story will turn same to YLZ. And the story will turn same to ZLX. What you will have here, you will have minus IH bar, and if you change the order, here, if you rightly remember the quantum mechanical box that I have been talking about, you will have a different story. Your IH bar will become positive, so you'll have Ly and X will give us IH bar, and then provided I have done the calculations right, I'm not sure, but I have tried my level best to do it. LZ and Y will give us IH bar, and then you have X and Z will give us IH bar. Okay, so this is how we calculate the commutation relations between the coordinates of the position and the coordinates of angular momentum. And you can see here that the two does not commute. That means nature is putting a constraint, to us to calculate accurately the position and angular momentum along y. The position along y and angular momentum along z. The position along z and angular momentum along x. So these operators do not commute in those directions, and can be generalized as the basis of Heisenberg's uncertainty principle for these pairs. Now, in a similar fashion, we would like to go for more calculations, but that should not be the case. We will not proceed it from here. But one thing I would like to tell is that in classical physics, what we have Poisson brackets, and we have Poisson brackets. So what you are doing is, if you have the position R and angular momentum L, and between them, what you do is you calculate the Poisson bracket. So what you do is you calculate, we have curly brackets for Poisson bracket. And to tell the story in quantum mechanics, what I have to do is I replace this Poisson bracket by a commutation. I replace it by a commutation, but I divide it by IH bar. So R and L. So what's going on? So if you have classical observables, you calculate their Poisson bracket as AB, and the quantum mechanical version of this Poisson bracket is a commutator, but you have to divide it by IH bar and the commutation between the operator A and B. This is how you can breach the classical use of word, the classical commutation with the quantum mechanical commutation. And the difference is a Poisson bracket in classical physics and a commutator in quantum mechanics. The two are related in such a way, in the right hand side, in the denominator of the commutator, I have IH bar. So with this, I would like to stop my conversation with you, my interaction with you. I hope you understand. I hope you realize the things that we have discussed over here. So thank you all.